Good morning, everyone. This talk focuses on zero-knowledge proof system, and this work was joined with Professor Guang. First, let's look what's zero-knowledge proof. Basically, zero-knowledge proof are some interactive process between two parties. One is proof and another is verifier. The prover claimed she knows some secret information, and she wants to convince the verifier. But the prover doesn't want to send the secret information directly to the verifier. So prover can construct a proof and send the proof to the verifier. After several rounds of interactions, the verifier output accept or reject. Zero knowledge is mean during the interactions, the verifier cannot learn anything about the secret information. Next is an example. The prover Alice. Alice claimed she owns some secret information, such as private key or some pre-image of hash values or some amounts of Bitcoin. She wants to convince the verifier that, but she doesn't want to send the secret information to verifier. So the prover can construct a proof and send the proof to the verifier. After several rounds of interactions, verifier output accept or reject. In general, zero-knowledge proof needs to satisfy several properties. One is completeness. Completeness is mean if the prover indeed knows some secret information, she can construct a proof and convince the verifier the statement is true with a very, very high successability. Next is soundness. Soundness is contrast completeness. It means if the prover cannot own this secret information, she cannot construct a proof and convince the verifier the statement is true with a high successability. The third is zero knowledge. Zero knowledge means except the validity of the statement, the verifier cannot learn anything during the interactions. Recent several years, zero knowledge proof has many applications. The first scenario is you can use zero knowledge proof to prove you are part of a group without revealing your identity. And also another scenario is you can use the zero knowledge proof to prove you know a solution to some puzzle without revealing the solution. And also you can prove you know the location of the hidden objects without revealing the actual location. And also zero knowledge has many applications in blockchain. First application is verify transaction without reveal the amounts. Recall that in practical, when you buy something, you just ask the seller the price and you compare your money with the price in height. And when your money is greater than the price, so you can buy it. Otherwise, you cannot buy it. This is the digital variance in cryptocurrency. The problem is we need to prove your money is greater than the price before you get access some internet service. There already have some business companies devoted to develop this. Another application is privacy preserving applications, such as DeFi. DeFi is decentralized finance. It doesn't need to rely on central financial intermediaries such as brokerages, exchanges, or banks. It allows some people to lend or borrow monies from each other. And another example is the blockchain-based e-voting system. Some big city in Japan has already used e-voting system based on blockchain. So another is the United States Postal Service applied some patents about the blockchain-based e-voting system, even though they are texting the system. Maybe the next United States president election, they will use the e-voting system. And the next application is verifiable outsourced computations. Because think about the scenario, our cell phone has a limited computing power. The server in general has a powerful computation ability, so we can delegate the computation by a powerful server. When the server finished the computation, it just sends the result to us. We need to check the result is correct or not. So we can use the zero knowledge proof to solve this. The third application is smart contracts. Think in traditional way, two parties to want to send a contract, they need a third trust party. Then they send the trust contract with the witness in the third party, and already use the blockchain. Such platform, some platforms such as Ethereum can do this more efficiently. So in Ethereum, you just upload the content to the platform. The platform will do other things for you. Also, the smart contract has many building features, such as it can save your time and has default backups. And also, it can avoid minor errors. It has many other applications. So next, look at what we did in the protocol. First, fix a file F, and C is arithmetic circuit. We can assume that the circuit contains only addition gate and multiply gate with fine 2. This is the example of small piece of circuit. In this circuit, we have 4 input and 6 gates, 3 addition gates and 3 multiply gates. The question is how a prover can convince a verifier CW equal to 1 without revealing any information about W. The W is all the private intermediate values. It's called a witness. So for every gate, we assume the gate is fine 2, so every gate has 2 input and 1 output. Let beta A and beta B the input value to this gate and beta C the output value to this gate. Then when G is addition gate, the constraint is equal to beta A plus beta B equal to minus equals beta C equal to 0. When G is multiply gates, the constraint become beta A times beta B minus beta C equal to 0. In this way, all the gates can be expressed as a linear constraint or quadratic constraints. on the witness bit. Linear constraint corresponds the addition gate. Quadratic constraint corresponds the multiply gates. So take this circuit as an example. We have 3 addition gates, so we have 3 linear constraints. Each corresponds one addition gate. So look at the first gate. The 2 input is alpha 1 and alpha 2. The output is beta 1. So this constraint is alpha 1 plus alpha 2 minus beta 1 equal to 0. And writes it in a matrix form have this. W contains all the input value and all the intermediate values. We have 3 constraints have 3 rows in matrix A plus. And also we have 3 multiply gates. We have 3 quadratic constraints. So look at the gate 4. The 2 input is beta 1 and beta 2, and the output is beta 4. So the second constraint is beta 1 times beta 2 minus beta 4 equal to 0. Also, in a matrix form, we can express the constraint in this form. The O dot is mean entry-wise product. Also, in order to get this vector, we need to construct a matrix AX, such as AX times W equal to X. In the same way, we need to construct AY and AZ. So in regular, the extended witness W contains 2 parts. The first part is the input value, and the second part is all the private intermediate wire values, and also has 4 linear constraints. One is text, the left input. The second is text, the right input. And the third is used to test the output. And the final is to test the addition gates. Also need to test the multiply gate, so we have a quadratic constraint. Totally, we have 4 linear text and 1 quadratic text. The length of witness is equal to the number of addition gates plus the number of multiply gates. So our first observation is we don't need to consider the addition gates. This idea is inspired by the QAP. So if we don't consider the addition gates, how we can deal with the addition gates? So the idea is we can express the output and of the addition gate as functions about the input, the output of other multiply output of multiply gates. So look at the first gate, it's the addition gate. So we can express the beta 1 as alpha 1 plus alpha 2. So we can directly write beta 1 and alpha 1 plus alpha 2. Also, the third gate can be expressed as the beta alpha 3 plus alpha 4. And the fifth gate, beta 5. Beta 5 is equal to beta 2 plus beta 3. And beta 3 is also equal to alpha 3 plus alpha 4. So we can directly write beta 5 as beta 2 plus alpha 3 plus alpha 4. So if we consider only the multiply gates, we don't need to consider the linear constraint again. Also, we don't need this. And the quadratic constraint will become this. We need to replace beta 1 with alpha 1 plus alpha 2, and also beta 5 with beta 2 plus alpha 3 plus alpha 4. So the quadratic constraint will need modify slightly also in a matrix form. So compare the Ligero. In our protocol, the extended witness contain two parts. The first part is the input value, but the second part is contain only the output of multiply gates. We don't need to consider the output of the addition gate. So linear constraint, we don't need the linear text. We only have three linear text. One is left input, another is right input, and the third is output. And we already need a quadratic constraint to text the multiply gate, but the entry in the x, y, z need to modify this slightly. So totally we have three linear text and one quadratic text. The length of witness equal to the number of multiply gates. We don't need plus the number of addition gates. And the second observation is because that we still have three linear check for the three vectors separately. So our second observation is we can do the linear check more efficiently. So we can do these three vectors simultaneously. We have three linear tests in a combined form. This is only just have one linear text. And later we will see if we combine the three linear text to one linear text, the communication will be reduced to 1/3. Next, we look at what's a linear text. Linear text is give a vector x and the matrix A, text whether A times x equal to 0. A simple probabilistic test for the claim AS equal to 0 is to check that the inner product x r and ax equal to 0 for random r. Of course, this is not true always. If ax not equal to 0, then this have a probability. The probability is equal to 1 over set of f. If the set of f is exponential in the security parameters, so this probability is negligible. This is a practical protocol. Matrix A in the prover just send a challenge vector S and and the prover computes the R equal to S transport times A. Each row is a RS code word, and also we need to query some columns. This is done for the X. So row check, we send R, we send S, and P send Q. Q is the RS code. The column check, except we check the Q satisfies some properties. We also need to query some columns. And also the quadratic test is give three vector x, y, z text x o dot y times minus z equal to 0. Also, the simple probability test for this is test x o dot y minus z equal to 0. Checks the inner product x and x o dot y minus z equal to 0 for random r. And indeed, this is not true always. If this is not true, also the soundness error is equal to 1 over set of f. So this also is negligible. Also, we write x as a matrix form, then interpolate each row as a RS code. In the same way, we can do this for y and z. So row check. The method is send the challenge vector r. The prover computes the q. Q is the rs code and send the rs code to the verifier. And also, a verifier needs to query some columns to check this inner product. Also, look at the linear text protocol and the quadratic text protocol. All the messages sent from the prover to the verifier is the RS code word. And also the soundness analysis is under the assumption of the message sent from prover to the verifier is RS code. So if we want to use this protocol in practice, we need to convert this protocol to a regular one. This means we need to text the message sent from prover to the verifier indeed is a RS code. So the problem is give you a matrix, how to test each row of the matrix is a code word, is a RS code. Because the RS code is a linear code, so for any linear combination, of course, the linear combination is the RS code. So the idea is very simple. So we just send the R and P compute the linear combination, send the Q to the prover, verifier check the messenger is the RS code and also query some T columns. Next is the comparison of R protocol with Ligero. In Ligero, their soundness is this, and in R protocol, we also improved their soundness, and this is the communication cost. Because that in our protocol we consider the multiply gates, so we also have just one linear text. So this is we don't have the number 4, and here is the length of the witness will be reduced greatly. And for the circuit of SHA-256 up to best of knowledge, the number of AND gates is equal to 22,000. The number of XOR gates is 91,000, and the inventor gate is 2,000. In Ligero, they consider all of these gates, so the total number is equal to roughly 111,000. If we consider the multiply gate, is namely the AND gate, so the length of witness is equal to 22,000. So the length of the witness can be reduced 1/5. This is a great improvement. Next is the argument size, prover and verify runtime comparison. In our protocol, argument size is 67 KB. It's just about 2/3 compared with Ligero. And the prover running time is 567 milliseconds. And the verifier running time is 197 milliseconds. The verifier running time is a great improvement. All the Pfizer is great, it's better than Ligero. So this is what we did in our protocol. Thank you, attention.